Welcome to the Whispering Scientist, your quiet corner of the internet where curiosity meets calm. This is a place to slow your thoughts, dim the noise of the day, and drift gently into wonder. Tonight's journey takes us far below the waves into a world where sunlight fades, pressure builds, and life has learned to thrive in the dark. We're exploring everything we know about the deep sea, the hidden half of our planet, where silence has shape and light is a living thing. Before we descend, I'd love to know where in the world you're listening from tonight. The comment section has become a small constellation of time zones and night owls, and it's always wonderful to see where this calm corner of the internet reaches. If this kind of peaceful science helps you unwind, a gentle tap on the like button really does make a difference. And if you'd like to join our growing community of sleepy explorers, please subscribe. To those who already have, thank you sincerely for being part of this slow, curious voyage. I hope this video isn't too interesting and keeps you awake, but if it does, at least you'll fall asleep a little wiser. So take a deep breath, let the noise above fade away, and imagine standing on the shore at dusk, watching the last light of day ripple across the water. The surface glows silver blue for a moment before the waves swallow the color. And that's where our story begins. At the thin, glittering edge of a world that stretches downward for nearly 11,000 meters, the ocean covers more than 70% of Earth's surface, yet most of it remains unseen. As daylight dances across the shallows, only a thin layer of the sea ever feels the warmth of the sun. Beneath that bright skin lies a world colder, darker, and older than human history, a place more alien than Mars, but right beneath our feet. The ocean is layered like a sleeping giant's blanket, each fold deeper, colder, and darker than the last. This descent isn't a journey through empty water, but through time itself. Every 100 meters brings you to layers formed decades ago. Every 1,000 meters carries you to waters untouched for centuries. We begin in the realm we know best, the sunlit upper ocean that reaches down about 200 meters. Here, light pours freely through water, clear as cathedral glass. Plankton drift like dust motes in golden shafts, turning sunlight into living matter. Fish scrawl quick silver lines through warmth, and turtles rise like slow punctuation to breathe before sinking again, unhurried. This is the ocean of movement and color, where most marine life glides through beams of light that still remember the sky. But our journey is downward, not outward, and so we begin to let the light thin. Sound changes first, the splash and chatter at the surface softening into a warm hush, the way a busy room quiets when a door closes. Light follows, reds fading almost immediately, then oranges and yellows until only a cool blue lingers, hanging on like a promise. The water grows steadier, its motions broad and slow, and the mind begins to match it, thought drifting without urgency. This is where physics begins to whisper its rules. For every 10 meters you descend, the weight of water adds another full atmosphere of pressure. At 100 meters, that extra weight would make your ears ache. At 1,000, pressure greater than 100 summers stacked upon you. It sounds severe, but here severity isn't violence. It's law, steady and even, shaping everything that lives with patient hands. Life that belongs to the deep has learned to avoid hollow spaces, trading fragile air balloons for gels, oils, and flexible tissues that yield rather than snap. As light drains away, our eyes recalibrate, then accept that sight is not always king. The ocean offers other senses here. Faint vibrations travel farther through water than they ever could in air, and even tiny motions leave signatures in the liquid medium. Temperature slips a degree at a time, not dramatic, just resolute. The warmth carried down from the sun gives way to a chill that sets the pace for everything. In cold water, metabolisms ease, movements economize, and lifespans extend till they seem less like clocks and more like weather. we pass a threshold you can feel, even if you've never been here. Above, the sunlit sea feeds itself in the morning. Below, twilight begins. You sense it in the way color narrows to a spectrum of blues, in the way forms lose their shadows and become suggestions. Creatures adapted to this edge wear light like jewelry, tiny measured sparks along flanks and fins, not for spectacle, but for signal. Here, illumination becomes language. A brief pulse meaning presence, another meaning deception, and a steady glow on a belly can erase a silhouette completely. The deep ocean is less like a place and more like a memory, vast, patient, and layered in silence. We drift past 200 meters, and the last warm threads of daylight pull free. Above us, a silver ceiling fades to slate. Below us, the water deepens to a blue so dark it feels like memory itself. Around this boundary, sight is still possible, just barely. Some creatures give up on vision entirely and become translucent whispers. Others carry their own lanterns, precise and efficient. The sea at this depth introduces itself without ceremony. It simply is, and in its being it invites us further into the zones that lie ahead, where twilight deepens into true darkness, and where the ocean's most remarkable secrets begin to unfold in the patient rhythm of the deep. The silver ceiling above us continues to darken as we drift deeper, the familiar warmth loosening its hold with each meter of descent. What began as a gentle dimming now becomes something more profound, a crossing into realms that operate by entirely different rules. The water around us grows denser, colder, and infinitely more patient. We are entering the mesopelagic zone, the twilight realm that stretches from roughly 200 to 1,000 meters, where the last whispers of sunlight struggle against the growing darkness. Here, blue light lingers the longest, scattering weakly through the water like the final notes of a song played in an empty cathedral. Red and orange have already been devoured by distance, leaving only these ghostly shades that grow fainter with every meter. The twilight zone is neither day nor night, but something suspended between them, a perpetual dusk where creatures have learned to live in the margins of visibility. Shapes lose their sharp edges here, and movement becomes the only sure sign of presence. This dim layer pulses with hidden travelers. Lanternfish drift in unhurried schools, their flanks dotted with measured points of light that switch on and off with the discipline of Morse code. Transparent shrimp hover like living glass between the currents, and squid hold their bodies at angles that catch the last whisper of glow from above. Many animals here keep to a simple rhythm that turns the whole zone into a living tide. Under cover of night, they rise toward the surface to feed in the rich waters above, then sink back down before dawn breaks. This daily migration represents the largest movement of life on Earth. Billions of bodies moving together in what feels like snow when you're close enough to touch it. Gentle, continuous, almost silent, the ocean's rules become clearer as light wanes. Predators peering up from below search for dark shapes outlined against the dim ceiling above. To disappear, many creatures grow their own soft belly lights, tuning them to match the glow from the surface. This counter-illumination erases shadows, turning bodies into nothing more than a continuation of water. Some squid can brighten and dim these lamps in real time, adjusting to passing clouds or the shifting phases of the moon far above. As we continue past the thermocline, not a wall but a slope where temperature drops quickly with depth, the water cools and steadies everything. Above, currents mix and tumble. Here, motion stretches into long, slow rivers. The chill settles into our bones, and metabolisms around us ease into lower gears. Even decay learns patience in this cold. A shadow passes too broad to be a fish and resolves into a colony of siphonophores, countless tiny bodies stitched into a single drifting animal that can stretch longer than a city bus, yet moves with the deliberation of falling silk. At around 1,000 meters, the last natural photons fail completely. We cross another invisible threshold into the Bath hypelagic zone, the midnight realm where no sunlight has ever reached. The water hovers just above freezing, black as velvet, and the pressure has grown immense, more than 100 times what we feel at the surface. Yet, it does not feel hostile so much as absolute, like a law written in water and weight. In this realm of perpetual midnight, creatures no longer reflect light, but create their own bursts of bioluminescence. They flash like Morse code across the abyss, each pulse carrying meaning in a silent conversation that spans the darkness. Some signals are warnings, bright flares that announce danger. Others are lures, gentle glows that whisper promises of food to the hungry. Still others are disguises, patterns that confuse predators or erase telltale shadows. It's a language written entirely in photons, spoken by creatures who have never seen the sun, yet understand light more intimately than anything on the surface. Food arrives mostly from above, exhausted by the journey. Marine snow falls without stopping, a slow rain of tiny particles, bits of plankton, fragments of shells, scales, and organic dust. Each flake is precious when you refuse to waste anything. Bodies here are made with soft materials, oil and gel instead of bone and air, so that pressure flows around them rather than crushing inward. Deeper still, we approach the abyssopelagic zone, stretching from 4,000 to 6,000 meters. The name abyss captures the feeling perfectly, a sense of bottomless depth. Down here, temperatures hover just above freezing in perfect consistency. Oxygen becomes scarce, and that gentle rain of marine snow becomes the primary currency of survival. The seafloor lies like a quiet field, rippled by slow currents where worms, sea cucumbers, and brittle stars work the sediment with the patience of gardeners, turning and tending it grain by grain. Even deeper, in the Hadal zone of the Great Trenches, life persists in pressure that exceeds 1,000 times the surface. But that realm awaits us later in our journey. For now, it's enough to feel how each layer prepares the next, how twilight teaches midnight to see without seeing, how midnight instructs the abyss in the art of patient survival. With every meter we descend, the weight above grows more persuasive, more defining. The water grows heavier not in aggression but in presence, and everything that lives here has learned to answer that presence with softness, with flexibility, with chemistry that holds its shape against gentle but relentless insistence. Ahead lies a deeper lesson in how this quiet pressure rewrites the very rules of existence, shaping life in ways the surface world has never imagined. The weight that has been quietly gathering around us with each meter of descent now reveals itself as more than sensation. It becomes the ocean's most patient architect, pressing in from all directions with a force that seems gentle until you realize its true magnitude. Every 10 meters deeper adds another full atmosphere of pressure, another invisible layer of weight that accumulates like slow-falling snow. At 1,000 meters, that weight has grown to more than 100 times what we feel at the surface. In the deepest trenches, it climbs beyond 1,000 atmospheres, the equivalent of 50 jumbo jets balanced on every square meter, pressing steadily inward without pause or mercy. Yet this crushing embrace doesn't feel violent down here. It feels absolute, like a law written in water and time. The ocean's pressure doesn't strike or squeeze. It simply exists, and everything that lives in its realm has learned to answer that existence with remarkable grace. The secret lies in understanding what pressure truly seeks. It hunts for empty spaces, for pockets of trapped air that can be compressed. Water itself, dense and nearly incompressible, flows around pressure like liquid stone. But air yields, shrinking under force, creating dangerous imbalances that can crush the unprepared. Imagine the difference between a rigid glass bottle and a soft balloon filled with water. Lower the bottle into the deep, and it will implode with a sharp crack when the pressure exceeds what its walls can bear. But the water-filled balloon simply adjusts, its flexible skin yielding to the force, while the incompressible water inside maintains its essential nature. This is the fundamental lesson that deep-sea life learned millions of years ago: flexibility over rigidity, adaptation over resistance, harmony over opposition. A snailfish drifts past us, its body so translucent it seems more like organized water than flesh. Found at depths greater than 8,000 meters, it appears impossibly delicate, with no scales, no swim bladder, no bones in any conventional sense. Its skeleton is mostly soft cartilage, its tissues filled with the same density as the surrounding water. What looks like fragility to surface eyes is actually sophisticated engineering. The crushing force that would flatten most creatures flows through this fish harmlessly, meeting no resistance because there are no rigid spaces to compress. The adaptations extend far beyond what we can see. At the molecular level, pressure becomes a constant threat to the delicate machinery of life. Proteins, those microscopic tools that power every cellular function, are precisely folded structures that can warp under extreme compression, losing their ability to work. Deep-sea organisms counter this with special compounds called piezolites, molecular guardians that stabilize proteins and keep cell membranes flexible even under crushing force. These pressure-protective molecules, often simple amino acids or compounds like trimethylamine oxide, act like internal scaffolding, ensuring that life's chemistry continues smoothly where physics itself seems to forbid it. We watch a giant amphipod scuttle across the seafloor, its segmented body the size of a dinner plate. Its shallow water cousins are tiny creatures no larger than rice grains, but down here, where pressure eliminates the luxury of gas-filled spaces, growing large becomes an advantage. Larger bodies distribute pressure more evenly, store more energy for the long waits between meals, and provide more space for the specialized chemistry that makes deep-sea survival possible. Even reproduction bends to precious influence. Eggs become precious, energy-rich packages designed for long journeys through the crushing depths. Larvae spend months drifting through layers of increasing pressure, their bodies gradually adjusting as they sink toward their adult homes. Each generation fine-tunes its relationship with the weight of water, evolving not to fight pressure, but to become part of it. The ocean's crushing embrace also shapes behavior in subtle ways. Movement becomes more deliberate, more economical. There are no sudden darts or frantic escapes here, no wasted motion. Everything flows with the measured pace of creatures who understand that energy is precious and patience is survival. A deep-sea skate glides past with wing-like fins that barely disturb the water, its flat body perfectly calibrated to life under pressure. For humans exploring this realm, pressure remains a formidable negotiator. Our submersibles must be engineered with the same principles that guide deep-sea life. The spherical crew compartments aren't chosen for aesthetics, but for physics, distributing pressure evenly across their surface to avoid weak points where the ocean might find purchase. Engineers fill these vessels with syntactic foam, countless microscopic glass spheres suspended in resin, strong yet light, capable of resisting immense pressure without crushing. In a poetic parallel, the same principle that protects a jellyfish's body, many small voids distributed evenly, also protects the machines we send to study them. As we continue deeper, approaching the abyssal plains where pressure reaches truly extreme levels, we begin to understand that the ocean's weight isn't an obstacle that life overcomes. It's a sculptor working with infinite patience, shaping every adaptation, every behavior, every biochemical pathway. The deep ocean's pressure doesn't destroy life. It refines it, creating forms of existence so perfectly balanced with their environment that they seem less like survivors and more like expressions of the water itself. But pressure works in partnership with another force, one that sets the tempo for everything the weight shapes. As the crushing embrace of depth defines what can live here, the steady cold that surrounds us determines how quickly that life unfolds, how slowly it moves, and how long it endures in this realm where time itself takes on new meaning. The weight that has been quietly shaping everything around us works hand in hand with another sculptor, one even more patient and persistent. Cold settles into the water like a steady hand, not harsh or sudden, but absolute in its presence. The temperature here hovers between 1 and 4 degrees Celsius, cold enough to numb human skin within minutes, yet perfect for a kind of existence that measures time not in heartbeats or seasons, but in centuries. If pressure is the deep sea's architect, then cold is its timekeeper, setting a rhythm so slow that moments stretch into seasons and seasons into geological ages. This chill transforms the very chemistry of life. Cold slows molecular reactions, which in turn slows metabolism, growth, and even decay. Every enzyme reaction, every cellular division, every nerve impulse moves through this frigid water like honey poured in winter. Where surface creatures burn through energy with the urgency of summer, deep sea life conserves it with the patience of glaciers. A fish that might live 10 years in warm shallows could endure for a century down here, its pulse so slow it seems suspended between moments. Some deep-sea corals add just millimeters to their skeletons each year, their growth rings marking not individual seasons, but centuries of constancy. The cold around us carries ancient memories. Every drop of this water once began its journey at the surface somewhere near the poles, where winter air chilled it until it grew dense and heavy. In the North Atlantic and around Antarctica, these surface waters sink like slow avalanches, sliding down continental slopes and spreading across the abyssal plains in a planetary circulation called thermohaline circulation. This underwater conveyor moves at barely a few centimeters per second, but over time it becomes Earth's deepest heartbeat. A single parcel of water can take more than 1,000 years to complete its journey through the deep ocean and return to the surface. The water flowing past us now last saw sunlight when Vikings sailed northern seas, when forests covered what are now cities, carrying the memory of ancient winters in its molecular structure. This thermal stability creates one of Earth's most unchanging environments. While surface waters swing between seasonal extremes, while storms rage and currents shift above, the deep maintains its temperature with the consistency of stone. Spring, blooms, summer warmth, and autumn decay mean almost nothing here. The seasons we know become irrelevant in a realm where time itself moves differently. This constancy allows life to evolve strategies impossible anywhere else, but it also demands adaptation at the most fundamental level. Cold water holds more dissolved oxygen than warm water, providing these slow-living creatures with a steady supply of what they need to survive. But the same chill that preserves also limits. Chemical reactions struggle in the cold, and the enzymes that drive life's processes must work harder to achieve the same results. Deep-sea organisms respond by producing cold-adapted enzymes, molecular machines built with flexible structures that can function efficiently even when heat is scarce. These enzymes are so refined that scientists study them to improve industrial processes, learning from millions of years of evolution's patient tinkering. The preserving power of this cold extends far beyond living tissue. Shipwrecks rest here. For centuries, their wooden beams and metal fittings protected by the absence of warmth and the bacteria that drive rapid decay. The Titanic, nearly 4,000 meters down, remains more intact than it would in any warmer sea, its gradual dissolution slowed to match the patient tempo of the deep. Even organic matter falls differently here, marine snow drifting in slow motion, taking weeks to travel distances that surface particles cover in hours. Yet the cold is not absolute everywhere. Along volcanic ridges and around hydrothermal vents, the Earth's heat creates sudden thermal oases where temperature can jump from near freezing to scalding within meters. these rare pockets of warmth, attract life from kilometers away, creating sharp gradients where moving closer means entering an entirely different world of chemistry and possibility. But away from these exceptions, the deep ocean's cold remains astonishingly constant, acting as Earth's great thermal stabilizer. As we drift deeper into this realm of eternal winter, we begin to understand that cold isn't just temperature here. It's time itself slowed and stretched until patience becomes the highest virtue and endurance the greatest achievement. The chill around us doesn't freeze life. It teaches it a different rhythm, one where every movement is deliberate, every heartbeat precious, and every adaptation refined across eons of stillness. But in this realm where sunlight is an impossibly distant memory and cold reigns supreme, life has discovered something remarkable. Where the sun's light cannot reach, creatures have learned to make their own, turning darkness into a living language. Written in gentle pulses of blue and green, each flash a word in conversations that span the endless night. Where cold has slowed time to its deepest rhythm and pressure has shaped every living form, the darkness around us reveals its most profound secret. Light returns to this realm, not borrowed from the distant sun or reflected from surfaces that remember sky but created from within, molecule by molecule, in one of nature's most elegant inventions. In the deep ocean where sunlight fades into memory, light becomes alive. It flickers from the flanks of fish, glows from jellyfish tentacles, and cascades in blue fire from disturbed plankton, transforming the eternal night into a living constellation of purpose and beauty. The chemistry behind this living light carries the simplicity of all profound truths. When a molecule called luciferin meets oxygen in the presence of an enzyme named luciferase, the reaction releases energy not as heat, but as a soft, cool glow of visible photons. It's the same fundamental process that makes fireflies shimmer on warm summer evenings. But here in the abyss, it unfolds across millions of species, from microscopic bacteria to colossal squid, turning darkness into a language written entirely in light. The color of this conversation is almost universally blue, and physics explains why with quiet precision. Blue wavelengths travel farthest through water, threading themselves through meters and sometimes tens of meters of liquid night, while reds and yellows are swallowed almost immediately by the dense medium. In a world where every photon is precious, blue becomes the universal vocabulary, the only hue that can carry meaning across the distances that matter in the deep. As we drift deeper, a small squid passes nearby, its body outlined in measured points of light that pulse with careful rhythm. These aren't random sparkles, but precise signals, each flash calibrated for survival. Along its belly, photophores glow steadily, matching the impossibly faint illumination filtering down from the surface world far above. This counter-illumination performs one of the ocean's most elegant tricks, erasing the squid silhouette against the dim ceiling above and making it invisible to predators scanning upward from below. It's camouflage by light, a vanishing act that seems to contradict logic until you understand the geometry of darkness. But not every display serves concealment. In the distance, a deeper flash draws our attention toward an anglerfish suspended, motionless in the current like a patient angler beside a midnight stream. From the top of its head grows a delicate rod tipped with a glowing bulb, a biological fishing line that sways gently in the water. The light emanates from symbiotic bacteria living within the lure, tiny partners that trade illumination for shelter, and nutrients in one of evolution's most successful collaborations. In the absolute darkness, that soft glow mimics a small drifting meal, and when curious prey swim close enough to investigate, the anglerfish's enormous mouth opens with lightning speed. Its patience weaponized, a trap that can wait motionless for hours until hunger brings opportunity within reach. Other creatures deploy light as desperate defense. A small shrimp, startled by our presence, releases a cloud of glowing particles that drift away like luminous smoke, the sudden flash confusing potential predators while buying precious seconds for escape. Nearby, an Atolla jellyfish demonstrates an even more dramatic strategy when threatened, creating a pulsing ring of blue light around its bell. This glowing alarm is designed to attract larger predators that might chase away whatever is attacking. The jellyfish, a brilliant example of calling for help in the only language the deep truly understands. The conversations happening around us are constant but subtle. Lanternfish communicate through rhythmic blinks, each species carrying its own distinct constellation of photophores arranged like living star charts along their flanks. These patterns allow recognition in the vast darkness, coordinate feeding movements among schools, and signal readiness for the rare encounters that lead to reproduction. Even the microscopic plankton participate, releasing waves of light when disturbed that ripple through the water like underwater aurora, a phenomenon that sailors in centuries past called the sea on fire as their ships carved glowing trails through the night. Some creatures have evolved private channels of communication. The stoplight loosejaw fish creates both blue and red light, but since red wavelengths cannot travel far in water, they remain invisible to most other eyes. This gives the loosejaw a personal flashlight that reveals prey without warning them, stealth by color that represents millions of years of evolutionary refinement. The vampire squid, despite its ominous name, performs one of the most graceful displays in the deep, turning itself inside out when threatened to reveal glowing blue spots along its arms that flash and fade like scattered stars, creating beauty from the simple need to survive. This living light connects scales almost beyond comprehension. From our vantage point in the deep, we're witnessing conversations that span entire ocean basins. Astronauts aboard the International Space Station occasionally observe vast patches of luminescent plankton stretching for hundreds of kilometers, turning sections of the sea into shimmering canvases visible from the edge of space. These displays remind us that bioluminescence isn't merely a local phenomenon, but a planetary one, connecting the deepest trenches to the cosmos through the simple act of making light from life. What strikes us most profoundly about this living illumination is its restraint. Every flash is measured, every glow precisely calibrated to its purpose. In a realm where energy arrives only as the faintest rain of particles from above, nothing is wasted on spectacle. The light appears, delivers its message with quiet efficiency, and fades back into darkness. Its communication distilled to its purest essence, life speaking to life in the most economical language possible. As we continue our descent through this galaxy of gentle signals, we begin to understand that the deep ocean's darkness isn't empty space but a medium rich with information, where creatures navigate not by sight but by the careful reading of living light. Yet even this remarkable adaptation depends on energy, and in a realm where sunlight never penetrates, life has had to discover entirely different ways to fuel its existence, drawing sustenance not from the sky above, but from the chemistry of the earth itself. The gentle conversations of living light that surround us carry a deeper mystery within their blue whispers. Each flash, each glow, each measured pulse requires energy to create, and in this realm where the sun's warmth is nothing more than ancient memory, we must ask where such power originates. The answer lies not in the sky we've left behind, but in the planet beneath us, in chemistry that seeps from stone and rises through cracks in the seafloor like the earth's own quiet breath. Here in the eternal darkness, life has discovered something revolutionary, something that changed our understanding of what living systems truly need. This is chemosynthesis, the art of eating stone, of drawing sustenance from the molecular conversations between minerals and water, where the surface world depends entirely on photosynthesis, on green plants capturing solar energy and weaving it into the foundation of every food web. The deep ocean has written its own rules, learned to feast on chemistry itself. The process unfolds with elegant simplicity around us. Hydrogen sulfide, methane and ammonia rise from deep within the seafloor, carrying potential energy locked in their molecular bonds. Specialized bacteria intercept these compounds, oxidizing them in carefully controlled reactions that release power. Where photosynthesis uses carbon dioxide and sunlight to build sugars, chemosynthesis simply substitutes chemical gradients for solar rays. It's like running an engine on whispers rather than roars, slow and efficient, entirely self-contained. We drift toward a rocky ridge where the water shimmers with invisible heat, and here we encounter one of evolution's most remarkable partnerships. Giant tube worms anchor themselves in dense colonies, some reaching 2 meters in length, their bright scarlet plumes unfurling like underwater flowers in the gentle current. These extraordinary creatures have no mouths, no stomachs, no digestive systems in any recognizable form. Instead, they've become living greenhouses, their bodies housing colonies of chemosynthetic bacteria in specialized organs. The worms extend their feathery red plumes into the mineral-rich water, drawing in hydrogen sulfide, carbon dioxide, and oxygen, which their bacterial partners then transform into organic nutrients. In return, the bacteria receive shelter, protection, and a steady supply of raw materials for their molecular alchemy. It's agriculture conducted at the cellular level, farming that happens within living tissue, with crops that grow on stone and water rather than soil and sunlight. The tube worms themselves become patient gardeners, providing controlled environments where their microbial partners can work their chemical magic, while the bacteria serve as internal farms, producing sugars and proteins that sustain their hosts through pure chemistry. Around these living towers, we discover entire communities that have never depended on the sun. Mussels and clams cluster along fractures in the rock, their gills modified to house similar bacterial symbionts that feast on methane and sulfides. They filter chemical-rich water through their bodies, concentrating the compounds their partners need while receiving nutrition in return. Pale crabs scuttle across bacterial mats that coat the rocks like living carpets, and ghostly fish drift through plumes of mineral-laden water, all participants in food webs built entirely on the planet's internal chemistry. The energy economics here operate on entirely different principles from anything we know at the surface. Photosynthetic ecosystems flood life with abundant power, hundreds of watts per square meter, driving rapid growth and dazzling diversity. But chemosynthetic communities survive on a trickle, energy millions of times weaker than the cascade falling from the sun. Yet in the deep ocean's patient realm, this gentle stream proves sufficient. The secret lies not in abundance but in constancy. A hydrothermal vent might flow for decades, a cold seep for millennia, providing reliable energy sources that allow communities to establish themselves across vast spans of geological time. We encounter these chemical oases in many forms. Some blaze with dramatic heat, where superheated water bursts from the seafloor, creating towering mineral chimneys that billow dark plumes. Others whisper with cold, steady leaks where methane and hydrogen sulfide seep slowly through sediment, supporting meadows of clams and forests of tube worms that persist for centuries. Each represents a different recipe of temperature, chemistry, and flow rate, and life fine-tunes itself to those exact conditions with remarkable precision. The discovery of these chemosynthetic worlds didn't just expand our catalogue of Earth's ecosystems, it revolutionized our understanding of life's possibilities. For the first time, scientists realized that living systems could exist entirely independent of sunlight, sustained by the chemical gradients that leak from the planet's interior. This revelation reaches far beyond our own world. If life can thrive on chemical energy alone, then the icy moons of the outer solar system, places like Europa and Enceladus with their subsurface oceans and rocky cores, suddenly become much more promising candidates for harboring life. As we continue deeper into this realm where chemistry replaces photosynthesis, we begin to understand how the fundamental scarcity of energy in the abyss has shaped not just how organisms feed, but how they've evolved into forms that seem to defy every principle governing life at the surface. The patient bacterial gardens we've witnessed represent just the foundation of the deep ocean's catalogue of impossible adaptations, where the crushing weight of water and the gift of endless time have sculpted creatures into shapes that blur the line between the magnificent and the ghostly. The bacterial gardens we've witnessed, with their patient chemistry drawing sustenance from stone and water, have shaped everything that lives around them in ways that challenge every assumption about what bodies should look like. In this realm where energy arrives as the faintest trickle and pressure rewrites the fundamental rules of existence, evolution has experimented with forms that seem to emerge from dreams rather than biology. The same scarcity that feeds chemosynthetic communities has sculpted their inhabitants into two seemingly opposite strategies. Some creatures have grown to astonishing sizes, while others have become nearly invisible, translucent whispers drifting through liquid night. A giant isopod lumbers into view, its segmented armor gleaming pale in our lights, a creature that looks like it crawled from the pages of ancient mythology. On land, its cousin, the common pillbug, barely reaches a few centimeters, but down here, this gentle giant stretches as long as a forearm. The transformation isn't random, but represents millions of years of evolutionary negotiation with the deep ocean's peculiar economics. In the perpetual cold, larger bodies lose heat more slowly, making them remarkably energy efficient. When food might arrive only once every few months, these giants can store enough reserves in their tissues to survive extended famines that would doom smaller creatures. Nearby, an amphipod scuttles through the sediment, its body the size of a human hand, where its shallow water relatives measure no larger than rice grains. This deep-sea gigantism follows a patient logic. Pressure eliminates the luxury of gas-filled spaces, so growing large becomes an advantage rather than a burden. Bigger bodies distribute the crushing force more evenly, travel farther on stored energy, and can afford to grow slowly, sometimes taking decades to reach maturity. In an environment where urgency means death and patience means survival, evolution has favored endurance over speed, building bodies designed not for quick reactions but for long, steady persistence through geological time. Yet alongside these gentle giants drift creatures that have chosen the opposite path entirely. A siphonophore passes like a living thought, its body stretching longer than a city bus, yet appearing as nothing more than a faint shimmer in our lights. Made up of countless individual organisms linked into a single colonial animal, it moves with the deliberation of falling silk, its translucent tissues allowing light to pass through unimpeded. In a world where there's nowhere to hide, invisibility becomes the ultimate camouflage. The transparency we observe isn't simply about avoiding predators, though that advantage remains crucial. These ghostly forms have solved the deep ocean's energy crisis through radical simplification. Made up to 95% water, their bodies match the density of the surrounding sea so precisely they can hover motionless without spending a single calorie. Rigid bones and dense muscles become expensive luxuries, replaced by flexible cartilage and gelatinous tissues that bend rather than break under pressure. Even the metabolic cost of producing pigments becomes wasteful when no natural light exists to reveal colors. The architecture of deep-sea bodies follows principles unknown at the surface. Neutral buoyancy, the deep's preferred state, is achieved through elegant chemistry rather than gas-filled bladders that would implode under pressure. Some creatures fill specialized organs with oils lighter than seawater, Others use compounds like ammonium chloride to reduce their overall density, creating living balloons that require no energy to maintain their position in the water column. A squid filled with just the right concentration of these solutions can drift motionless for hours, its body perfectly calibrated to neither sink nor rise. We encounter a deep-sea anglerfish suspended in the current, its body appearing almost unfinished with loose, flabby skin and underdeveloped bones. To surface eyes, it looks fragile, even diseased, but this apparent weakness represents millions of years of evolutionary refinement. Every aspect of its anatomy has been streamlined for existence under crushing pressure, in perpetual cold, and on the barest minimum of energy. When scientists bring these creatures to the surface, the sudden drop in pressure leaves them looking deflated and distorted, their bodies designed so perfectly for the deep that they cannot exist anywhere else. The giant squid that occasionally appears in these depths embodies both extremes simultaneously. Reaching lengths of over 12 meters, it represents the ocean's capacity for magnificent scale, yet its body consists almost entirely of muscle and water, soft tissues that yield to pressure rather than resist it. These creatures are living lessons in physics and patience, colossal animals with the delicate anatomy of jellyfish, designed by pressure and perfected by time across eons of darkness. Even reproduction adapts to these extreme conditions. Many deep-sea creatures produce large, energy-rich eggs that can survive months drifting through crushing depths. Others release larvae that spend years traveling through the water column, their bodies gradually adjusting to increasing pressure as they sink toward their adult homes. In places where chemical oases go silent, fragments of wood or whale bones can ferry entire communities onward, slow arcs carrying life from one harbor of chemistry to the next. As we drift among these giants and ghosts, we begin to understand that the deep ocean rewards dual-purpose design. Every adaptation serves multiple functions. Oil-filled livers provide both buoyancy and energy storage. Translucent skin offers camouflage while reducing metabolic costs. And bioluminescent organs create both communication and deception. Nothing here is wasted on spectacle alone, but these remarkable bodies, shaped by pressure and scarcity into forms of impossible grace, must also navigate a world where sight means little and distance means everything. In the endless darkness that surrounds us, creatures have learned to perceive their environment through entirely different senses, turning the ocean itself into a vast acoustic landscape where sound becomes sight and vibration becomes the map that guides life through liquid night. The giants and ghosts we've witnessed, their bodies sculpted by pressure into forms of impossible grace, must navigate a world where their carefully evolved transparency and bioluminescent signals can only reach so far. In this realm where sight dissolves into memory, the ocean itself becomes the instrument that carries meaning across distances that light could never hope to traverse. Sound slips into the role that vision once held, mapping space, revealing motion, and stitching lives together across water far wider than any eye could span. The physics that governs this transformation is elegantly simple, yet profound in its implications. Water conducts sound with remarkable efficiency, its molecules packed roughly 800 times more densely than air, creating a medium where vibrations pass from neighbor to neighbor at speeds 4 times faster than anything possible in our atmospheric world. A single, low-frequency note can travel thousands of kilometers through the deep ocean, threading between layers of warm and cold water, like a whisper navigating an enormous cathedral. High-frequency sounds fade quickly, absorbed by water's chemistry, and scattered into heat, so the deep favors the long, patient voices that can cross continents without tiring. Around us, creatures have transformed their entire relationship with space through acoustic perception. Many deep-sea fish carry lateral line systems, networks of sensitive pores along their flanks that detect the faintest pressure changes in the water. These living seismographs can sense the movement of other animals from remarkable distances, reading the signatures of fins cutting through liquid or bodies displacing the medium around them. Some fish have evolved specialized bones linked to their swim bladders, turning internal air spaces into microphones perfectly tuned to the sea's pulse. Even a grain of sand settling on the seafloor creates ripples that the right listener can interpret, transforming the ocean into a vast early warning system where nothing moves unnoticed. A sperm whale's distant call reaches us through the darkness, a series of clicks so powerful they could stun prey at close range, yet here they arrive as gentle pulses carrying information across an entire ocean basin. These magnificent creatures use echolocation with precision that surpasses our most sophisticated sonar systems, sending out rapid bursts of sound and reading the returning echoes with extraordinary detail. Each click paints a three-dimensional picture of the world around them, revealing not just shape and distance, but texture, density, and internal structure. A sperm whale can detect a giant squid through pitch-black water at depths where no photon has penetrated in millions of years, its acoustic vision more precise than any camera could ever be. The ocean's natural symphony layers itself around us in frequencies both ancient and eternal. Wind and waves at the surface create a constant susurrus that filters down through the water column like distant applause. Storms contribute deep, rolling notes that travel for thousands of kilometers, their acoustic signatures readable as weather. Maps by creatures who have learned to interpret pressure and rhythm. In polar waters, the cracking and grinding of ice adds sharp percussion to the mix. Underwater thunder created by the planet's frozen breath, shifting and carving in slow-motion violence. Life adds countless voices to this acoustic landscape. Coral reefs, though distant from these depths, contribute a constant chatter of clicks, snaps, and grunts from shrimp whose claw snaps create cavitation bubbles that collapse with tiny bangs. Fish drum by vibrating their swim bladders, creating resonant notes that travel through water like organic church bells. Others grind their teeth, croak, or hum, each species contributing its own frequency to an endless conversation that spans the globe. But it's in the deep ocean where sound truly replaces sight as the primary sense. Here, only the low, resonant tones survive the journey from distant sources, creating natural sound channels where certain frequencies travel with minimal loss across entire basins. Whales have learned to use these acoustic highways, their calls following underwater valleys and temperature gradients that focus and amplify their voices. A song begun off California might be heard near Japan, carried by layers of water that act as waveguides, turning the Pacific into a single, vast communication network. We drift past deep-sea fish whose eyes have become vestigial afterthoughts, their lateral line systems extending across their bodies like living radar arrays. In absolute darkness, these creatures see more clearly through sound than most surface animals do through light, reading seafloor texture, current movement, and the presence of other life through vibrations alone. Their world exists as texture and rhythm, a constant interplay of echoes and pressure waves that paint landscapes invisible to any other sense. Human exploration of these depths relies on the same principles. Our sonar systems send pulses and read returning echoes using sound to map seafloor features no light could reveal. Through patient acoustic archaeology, we've discovered most of what we know about the ocean's hidden topography, its ridges and trenches revealed not by illumination, but by the careful reading of echoes bouncing off stone and sediment. Yet our mechanical voices have complicated this ancient soundscape. Ship engines and seismic surveys add artificial noise that can mask whale songs across vast distances, creating challenges for creatures that evolved in a quieter world. The deep ocean now carries the mechanical heartbeat of human activity, reminding us that even in the most remote places, our presence echoes. As we continue deeper, the ocean's voice gradually thins toward the seafloor, where sound encounters its final destination in the vast, patient plains that stretch between underwater mountains, creating landscapes that receive every acoustic message and transform them into the gentle rhythm of falling sediment. The ocean's voice that has carried us through layers of liquid conversation gradually settles into its deepest register as we approach the seafloor, where every echo and call eventually finds its resting place. Sound doesn't disappear here, so much as transform, absorbed by vast fields of sediment that stretch beyond any horizon, creating the largest and perhaps quietest habitat on Earth. These are the abyssal plains, where the acoustic symphony above meets its gentle conclusion in a silence so complete it feels like the planet holding its breath. The sea floor spreads beneath us like an ancient manuscript written in the finest script, its surface sculpted into gentle ripples by currents so slow they barely disturb individual grains. This is not the dramatic landscape of underwater mountains or thermal vents, but something more profound in its simplicity, a world built entirely from patience, where every particle has traveled for weeks or months to reach this final destination. The plains cover more than half of Earth's surface, yet remain among its least visited places, an endless expanse of soft sediment that receives everything the ocean has to offer and transforms it with infinite care. Marine snow falls here without pause, each flake a tiny relic of life from the sunlit waters far above. Fragments of dead plankton, microscopic pieces of shells, scales, and organic dust drift downward through all the zones we've traversed, growing smaller and more fragile with each meter of descent. By the time they settle on the seafloor, these particles are whispers of what they once were, yet they represent the sole sustenance for an entire world. This gentle rain accumulates grain by grain into layers that record the ocean's history like pages in an endless book, each stratum holding traces of ancient climates and the chemical signatures of events that shaped the planet when continents were young. Life here moves to match this unhurried rhythm, creating what can only be called an economy of courtesy. A sea cucumber glides past us with the deliberation of flowing honey, its soft body perfectly designed to process vast quantities of seafloor material in search of the few organic molecules scattered within. These gentle farmers plow through the mud with infinite patience, leaving behind neat trails that crisscross the bottom like the tracks of underwater tractors, each furrow representing hours of methodical feeding on particles too small for most creatures to detect. Brittle stars spread their delicate arms into the faint current like living flowers, their movements so economical they seem almost motionless. Their calcium carbonate bodies grow with geological patience, adding microscopic layers year after year until some individuals become older than human civilizations. Nearby, a grenadier fish drifts above the sediment with measured wing beats, its large head and sensitive barbels sweeping the mud like living radar, reading chemical signatures invisible to any other sense. This constant rearrangement of sediment by countless burrowing creatures creates the seafloor's quiet metabolism. Bioturbation, as scientists call this process, is the abyss equivalent of forest roots and insects turning soil. Worms tunnel through the mud in corkscrew patterns, aerating it and mixing nutrients in networks that benefit entire communities. Their burrows create channels that allow oxygen and organic matter to penetrate deeper into the seafloor, supporting vast populations of microbes that would otherwise suffocate in the airless depths. The monotony occasionally breaks with gifts from the geological past. Manganese nodules litter portions of the seafloor like dark potatoes, each one grown layer by microscopic layer around tiny fragments of debris over millions of years. These metallic spheres are time capsules of ocean chemistry, recording the slow breathing of the planet in concentric rings of accumulated minerals. Around them, deep-sea sponges anchor themselves to the only hard surfaces available, filtering hundreds of liters of water daily with no sound, passing the ocean through their bodies as if reading it molecule by molecule. The abyssal plains serve as more than habitat. They function as Earth's deepest archive and climate regulator. Each year, trillions of particles settle here and become buried beneath new layers of silt, locking away carbon that might otherwise return to the atmosphere. This silent service, carried out by gravity and time, helps stabilize the planet's climate across geological ages. The seafloor breathes slowly, processing organic matter and cycling nutrients that eventually support every other ocean ecosystem we've encountered. Rare disturbances can transform these quiet plains in moments. Distant earthquakes trigger underwater landslides that send turbidity currents racing across the seafloor like rivers of liquid mud, carving channels and redistributing sediment across distances that swallow maps. These events arrive perhaps once in a lifetime for the creatures here, but when they do, they reshape entire regions and create new opportunities for colonization by the patient pioneers of the deep. As we drift across these endless fields of silence, we begin to understand that the abyssal seafloor isn't empty space between more dramatic features. It's the ocean's foundation, the stable platform where every chemical cycle begins and ends, where the memory of surface life is slowly transformed into the building blocks of future ecosystems. The silence here isn't absence but presence, the sound of the planet resting, processing, and gently turning over its memories grain by grain. But even these vast, patient plains eventually yield to deeper forces. The level horizon ahead begins to lean almost imperceptibly, then more decisively, as the sediment gives way to steeper slopes. The seafloor that seemed to continue forever now folds into itself, gathering momentum toward the most profound scars on Earth's surface. We are approaching places where the planet literally swallows itself, where trenches plunge to depths that challenge every assumption about what life can endure, and where the quiet we've known prepares to become something even more absolute. The level horizon that has guided us across the abyssal plains begins to tilt, first so subtly it feels like imagination, then unmistakably, as the seafloor curves away beneath us with the inevitability of planetary mechanics. What seemed to stretch forever now folds into itself, gathering momentum toward the most profound scars on Earth's surface. The sediment that once lay, even as dust now slides in patient sheets, pointing toward a darkness that speaks of forces far greater than the gentle accumulation of marine snow. We are descending toward the Hadal zone, named for Hades, the underworld of ancient mythology, where the planet quite literally swallows itself in trenches so deep they could hide mountains. These are not mere cracks in the seafloor, but immense wounds in the Earth's skin. Valleys carved not by rivers or glaciers, but by the slow-motion collision of continents across millions of years. The Mariana Trench, deepest of them all, plunges nearly 11,000 meters beneath the surface, deeper than Mount Everest is tall. The Peru-Chile Trench stretches along the entire western coast of South America like a liquid canyon, while the Japan and Kuril Trenches mark where the Pacific Plate slides beneath the continental margins of Asia in geological ballet. Each represents a place where oceanic crust, heavy with age and minerals, surrenders to the inexorable pull of the mantle below through a process called subduction, the planet's way of recycling itself, grain by grain, across eons. The geometry becomes dramatic as we continue our descent into this underworld doorway. The walls rise steeply on either side, creating a narrow valley that curves like the blade of a crescent moon, rocky faces scarred by occasional landslides where sediment breaks free and tumbles into the depths with geological patience. The sense of scale overwhelms as we pass 6,000 meters and enter the true Hadal realm, a landscape carved by forces that operate on timescales where human history becomes less than a heartbeat. Far below lies the Hadal floor, a ribbon of sediment and rock just a few kilometers wide, yet stretching for hundreds of kilometers. The most remote habitat on Earth, cut off from sunlight, tides, and almost every influence of the surface world. At 8,000 meters, then 9, the pressure has grown beyond easy comprehension. More than 800 times what we feel at the surface, yet life persists with remarkable tenacity. A pale snailfish glides past our lights, its body so translucent it appears made of organized water rather than flesh. This is Pseudoliparis, discovered only recently in the deepest reaches of these trenches, living where no vertebrate was thought capable of survival. The creature appears impossibly delicate, lacking scales, swim bladder, or bones in any conventional sense. Its skeleton consisting mostly of soft cartilage, its tissues filled with compounds that match the density of surrounding water perfectly. What looks like fragility represents millions of years of evolutionary negotiation with physics itself. Inside these animals, proteins that would crumple under compression are guarded by specialized molecules called piezolites, molecular scaffolding, that prevent cellular machinery from warping under extreme force. Trimethylamine oxide accumulates in their cells like quiet armor, ensuring that the chemistry of life continues smoothly where the laws of surface existence would seem to forbid it. The fish's strength lies not in defiance but in agreement, a perfect compact with the weight it inhabits. The isolation of these trenches creates biological islands separated by vast distances and impossible barriers. Each trench harbors its own unique species, creatures found nowhere else on Earth, adapted specifically to their particular combination of depth, pressure, temperature, and chemistry. Scientists call this Hadal endemism, evolution, proceeding in separate laboratories where each valley operates on its own timescales. An amphipod that thrives in the Mariana Trench cannot survive in the Tonga Trench despite similar conditions, because millions of years have fine-tuned each population to its exact environment. At 10,000 meters, approaching Challenger Deep, the ultimate destination of our descent, the pressure exceeds 1,000 times that at the surface, equivalent to 50 jumbo jets pressing on every square meter. The water itself behaves differently under such compression, its molecules forced closer together, altering fundamental properties. The sediment at the bottom feels fine as powder, accumulated over eons from particles that began their journey in the sunlit waters we left behind. Every movement sends clouds drifting upward where they hang suspended for hours, creating temporary galaxies of disturbed mud that catch and scatter our lights. Yet even here, in Earth's deepest accessible realm, life endures with quiet determination. Xenophyophores, single-celled organisms that grow as large as dinner plates, construct delicate shells from collected debris. Amphipods scuttle through the ooze with the patience of creatures perfectly adapted to conditions that would destroy almost any other form of life. The trenches serve as natural archives where each layer of sediment contains traces of ancient climates, volcanic eruptions, and cosmic events, making them libraries of planetary history written in chemistry and time. As we hover at the edge of this ultimate abyss, we understand that the Hadal zone represents more than depth. It embodies the planet's capacity for extremes, places where life tests its absolute limits and discovers that even impossible conditions can become home. But these remarkable trenches, defined by crushing pressure and isolation, represent only one expression of Earth's chemical creativity. Rising from other parts of the seafloor, where tectonic forces create entirely different conditions, we will encounter places where the planet's internal heat meets the crushing cold of the deep. creating oases of energy that transform darkness into abundance through the alchemy of fire and water. From the ultimate depths, where pressure reigns as the ocean's most absolute law, we begin our journey toward places where entirely different forces shape existence. The crushing silence of the trenches gives way to something unprecedented in our descent, the first whispers of heat we've encountered since leaving the sun-warmed surface thousands of meters above. Here, along the great mid-ocean ridges that snake around the globe for more than 60,000 kilometers, the Earth's internal fire meets the crushing cold of the deep in one of nature's most dramatic contradictions. These underwater mountain ranges mark where the planet's crust spreads apart with geological patience, opening gaps where molten rock pushes upward from the mantle below. Seawater seeps into these fractures, penetrating deep into the crust where it heats to hundreds of degrees Celsius, becoming infused with dissolved minerals and gases drawn from the Earth's interior. This superheated, chemically rich fluid then surges back toward the seafloor under immense pressure, creating hydrothermal vents, the ocean's hidden forges where geology and biology intertwine in a dance of heat, chemistry, and impossible life. When this scalding water, reaching temperatures of 400 degrees Celsius, meets the near-freezing seawater above, the contrast creates instant transformation. The dissolved minerals precipitate in moments, solidifying into towering chimneys that billow dark plumes into the surrounding darkness. These structures, known as black smokers, can rise as tall as 10-story buildings, their columns growing and collapsing over years like living volcanoes constructed entirely of metal and stone. The immense pressure at these depths prevents the superheated water from boiling, allowing it to remain liquid at temperatures that would create steam at the surface. Not every vent announces itself so dramatically. Diffuse vents release gentler flows of mineral-rich water that emerge as shimmering, almost invisible currents threading through the rocky landscape. These quieter expressions lack the theatrical black plumes, but create equally vital oases of life, their moderate gradients of heat and chemistry providing perfect conditions for creatures that prefer subtlety to spectacle. Together, black smokers and diffuse vents create a patchwork of microhabitats, each offering its own precise recipe of temperature, acidity, and dissolved elements. The true miracle of these places lies not in their dramatic appearance, but in their chemistry. Where sunlight cannot penetrate, chemical gradients become the primary source of energy for entire ecosystems. The vent fluids carry compounds like hydrogen sulfide, methane, and various forms of iron, all capable of being oxidized to release energy. Microscopic bacteria and archaea intercept these chemicals, performing chemosynthesis by stripping electrons from molecular bonds to power their metabolism. Instead of green chlorophyll capturing solar photons, these organisms use specialized enzymes to harvest energy from stone and water, creating the foundation for food webs that have never depended on the sun. Around these microscopic chemical engineers, remarkable communities flourish with astonishing speed and density. Giant tube worms anchor themselves in dense colonies, some reaching 2 meters in length, their bright scarlet plumes unfurling like underwater flowers in the mineral-rich currents. These extraordinary creatures possess no mouths, no stomachs, no digestive systems in any conventional sense. Instead, they have become living greenhouses, their bodies housing colonies of chemosynthetic bacteria in specialized organs. The worms extend their feathery plumes into the vent water, drawing in hydrogen sulfide, carbon dioxide, and oxygen, which their bacterial partners transform into organic nutrients through pure chemistry. Vent mussels and clams adopt similar strategies, harboring symbiotic bacteria within their gills and feeding them sulfide-rich water in exchange for nutrition. Some shrimp species carry their microbial partners directly on their shells, grazing them like underwater gardeners tending microscopic crops. Pale crabs scuttle across bacterial mats that coat the rocks like living carpets, while ghostly fish drift through plumes of mineral-laden water, all participants in food webs built entirely on the planet's internal breath. These vent communities grow with remarkable speed, often blooming within months after a new vent opens. But their world remains fundamentally unstable. A vent can vanish overnight if geological shifts redirect the flow or cause chimneys to collapse. The animals that call these places home must adapt not only to extreme heat and crushing pressure, but to constant change. Many species produce larvae that drift with deep currents for months, searching for new active vents where conditions remain suitable for colonization. The discovery of hydrothermal vents in 1977 revolutionized our understanding of life's possibilities, proving that entire ecosystems could exist independently of sunlight. These sites serve as windows into Earth's early history, their conditions resembling what scientists believe existed on the young planet billions of years ago when the first living cells may have formed on mineral surfaces in hot, chemical-rich water. Yet even as we marvel at these oases of fire and chemistry, we sense that the planet's creativity extends beyond dramatic heat and towering chimneys. Elsewhere on the seafloor, gentler expressions of Earth's chemical breath create different kinds of hidden gardens, places where methane and hydrogen sulfide seep quietly through sediment, sustaining communities built not on fire but on patience, not on spectacle but on the steady persistence of cold chemistry working its quiet magic across centuries. The dramatic theatre of hydrothermal vents, with their towering chimneys and scalding plumes, represents only one expression of the Earth's chemical breath. As we drift away from these underwater forges, the water around us settles back into its patient constancy, and we encounter places where the planet's creativity takes an entirely different form. Here, energy does not erupt or roar, but seeps, whispering up through sediment with the patience of geological time itself. These are the cold seeps, the ocean's quiet embers, where methane and hydrogen sulfide leak gently from the seafloor in processes that can persist not for decades, but for millennia. At first glance, a cold seep might appear unremarkable, perhaps just a shimmer in the water that suggests movement without drama, or a pale patch in the endless grey sediment. But approach more closely, and we discover one of the ocean's most surreal phenomena: brine pools, underwater lakes resting at the bottom of the sea. These dense, salty basins collect in depressions on the seafloor, their surfaces rippling like liquid mirrors beneath the crushing weight of the ocean above. The water within is so heavy with dissolved salts and gases that it refuses to mix with the seawater around it, creating a sharp boundary between two liquid worlds that seems to defy every intuition about how water should behave. These underwater lakes appear oily or glassy under our lights, their surfaces reflecting illumination like ponds on an alien moon. Some shimmer with an almost metallic sheen, while others remain perfectly clear, their edges so sharp you could draw a line through the water itself. Small fish occasionally dip down toward these pools, cross the invisible boundary, and drift back up, stunned, reminded too late that this lake within a lake is not meant for them. The chemistry here can be lethal to most marine life, yet the edges of these pools teem with creatures that have learned to harvest the contrast between these two realms. The source of this strange chemistry lies in the behavior of methane under the ocean's extreme conditions. As methane rises from deep within the Earth's crust, it encounters the crushing pressure and near-freezing temperatures of the deep sea, combining with water molecules to form methane hydrates, crystalline structures sometimes called fire ice. These remarkable substances look like dirty snow or clouded glass, yet they burn with a clear flame when brought to the surface. The hydrates form extensive deposits within seafloor sediments, stabilizing them like geological cement while storing more energy than all known fossil fuel reserves combined. When geological forces disturb these frozen deposits, methane escapes in streams of bubbles that rise through the water column like strings of silver pearls moving upward through liquid night. These seeps create oases of chemical energy that support entire ecosystems built on patience rather than spectacle. Bacterial mats spread across the seafloor like underwater meadows, their white and golden filaments processing methane and sulfide with microscopic precision, transforming toxic gases into the organic matter that feeds everything above. Around each seep, life gathers with quiet determination. Tube worms anchor themselves along fractures where seepage is strongest, their scarlet plumes drawing in the compounds their symbiotic bacteria need to create food from chemistry alone. Mussels and clams burrow into the sediment, positioning their gills to expose internal bacterial partners to the mineral-rich fluids below. These animals cluster along the boundaries of brine pools like shoreline communities, harvesting the chemical gradients where two worlds meet. The stability of cold seeps creates opportunities for remarkable longevity that hot vents cannot offer. Where hydrothermal communities must constantly adapt to changing conditions as vents shift and die, cold seep ecosystems establish themselves across vast spans of time. Some communities persist in the same locations for thousands of years, their shells accumulating in quiet reefs built not of coral but of generations living and dying in the same patient chemistry. These are monuments to endurance, archives written in calcium and time. The microbes that consume methane at these seeps serve as more than ecosystem engineers. They act as planetary guardians, intercepting greenhouse gases before they can escape to the atmosphere. Without these microscopic communities working their quiet alchemy, vast quantities of methane might rise through the ocean and contribute to climate change. In consuming these gases, they help regulate the planet's atmospheric balance through patient work that spans centuries. As we hover at the edge of one brine pool, watching its surface ripple like liquid glass while methane pearls drift upward through the darkness above, we understand that the deep ocean's creativity extends far beyond what sunlight can power. Where vents burn bright and brief like underwater stars, seeps glow dim and enduring like distant galaxies, each representing different solutions to the same fundamental challenge of drawing sustenance from stone and water. But not all abundance in the deep rises from below through chemistry and heat. Sometimes the greatest gifts fall from above, arriving not as seeping gases or mineral-rich water, but as entire forests of nutrition descending through the darkness. When that happens, the quiet plains transform, and the deep writes one of its most moving stories in the language of bone and time, where death becomes the foundation for decades of life. The patient chemistry of cold seeps, with their gentle persistence measured in millennia, prepares us for abundance that arrives through entirely different means. Where methane and hydrogen sulfide whisper up through sediment to sustain communities across geological ages, sometimes the deep receives gifts that fall rather than rise, transforming barren plains into thriving oases not through the slow breath of the planet, but through the final journey of its largest inhabitants. When a whale dies at sea, its story enters a new chapter rather than reaching conclusion, and that chapter will be written in bone and time across decades of patient transformation. The descent begins as a quiet avalanche of nourishment. The massive body that once moved through sunlit waters with grace and song, now turning slowly in the water column as gases escape and weight takes hold. This is no mere falling object, but a drifting island of concentrated energy, carrying within its tissues the accumulated wealth of a lifetime spent feeding in the ocean's productive surface layers. Long before it settles on the seafloor, the sea has sensed its approach. Hagfish emerge from their burrows like pale ribbons drawn by ancient instincts, while sleeper sharks materialize from the darkness to join a procession that spans every depth we've traversed. When the carcass finally comes to rest on the abyssal plain, It triggers one of the most remarkable ecosystem transformations in the natural world. The usual scarcity of the deep gives way to sudden, overwhelming abundance that will reshape this patch of seafloor for the next 50 to 100 years. The transformation unfolds in 3 distinct acts, each lasting years and supporting entirely different communities of life. A slow-motion drama of renewal played out in the planet's deepest theaters. The scavenger stage erupts with activity that seems almost frantic compared to the abyss's usual tempo. Giant isopods arrive in their dozens, their segmented armor gleaming as they work across the carcass with methodical precision. Hagfish burrow directly into soft tissues, creating tunnels that release clouds of organic matter into the surrounding water. Sleeper sharks glide in and out of our lights, their movements deliberate as they claim portions of this unexpected feast. Within months, the recognizable form disappears, consumed by creatures whose entire existence centers on these rare windfalls, energy that once powered migrations now dispersing into hundreds of smaller lives. As the skeleton emerges, cleaned of flesh but saturated with oils and fats representing decades of stored energy, the enrichment stage begins with quieter purpose. These lipids seep slowly into the surrounding sediment, creating a chemical halo of fertility that transforms barren mud into rich substrate. Polychaete worms lace through the bones themselves, while clams and snails cluster around the framework, drawn by the steady release of organic compounds. The seafloor darkens with enrichment several meters beyond the skeleton's outline, like the shadow of abundance cast by concentrated life. The final transformation proves most mysterious and beautiful. Deep within the massive bones, bacteria begin breaking down the remaining lipids, releasing hydrogen sulfide through the same chemistry that powers hydrothermal vents and cold seeps. The whale fall creates its own chemosynthetic ecosystem, turning from conventional nutrition into something far more sophisticated. Tube worms appear as if remembering the scent from volcanic worlds, while specialized mussels settle on the bones themselves, hosting symbiotic bacteria that feast on sulfur compounds leaking from calcium chambers. Among these remarkable inhabitants lives one of evolution's most elegant solutions to an impossible niche. The Ossidax worm, discovered only recently, has no mouth or stomach, instead growing root-like projections that penetrate whale bones and house symbiotic bacteria. Together, worms and microbes dissolve the fats trapped within the calcium matrix, sharing nutrients while slowly transforming solid vertebrae into delicate lacework. Its decomposition as embroidery, patient and precise, turning structure back into possibility, molecule by molecule. These bone islands serve as more than local oases. They function as stepping stones across the vast emptiness of the abyssal plains. The same species that colonize whale falls also inhabit hydrothermal vents and cold seeps, their larvae carried by deep currents between chemical havens separated by thousands of kilometers. Each whale fall becomes a link in an underwater archipelago of abundance, connecting distant ecosystems through the slow dispersal of microscopic travelers who carry genetic messages between islands of energy. To drift above one of these sites feels like entering a cathedral built from calcium and time. The ribs and vertebrae have become foundations for entire neighborhoods, draped in bacterial mats and surrounded by creatures moving with the careful reverence of those who understand they inhabit sacred space. Worms sway like underwater grass between the bones, while crabs navigate the architecture with deliberate steps, their movements somehow subdued by the gravity of transformation they witness. The whale's final gift demonstrates the deep ocean's fundamental principle. Nothing is wasted, only transformed. Energy changes hands across decades but never disappears, flowing from surface productivity to abyssal communities through the patient alchemy of death and renewal. Each skeleton becomes both monument and foundation, a reminder that in the deep sea's economy of scarcity, even endings become beginnings through the quiet miracle of time. Yet these dramatic oases represent only one expression of the abyss's architectural possibilities. Elsewhere on the seafloor, other builders work with even greater patience, constructing frameworks that endure not for decades, but for millennia, raising branching cathedrals from living stone that transform darkness into habitat through the slow accretion of centuries. The cathedral of bone we've witnessed, with its decades of patient transformation, represents only one form of architecture in the abyss. Where whale falls bloom briefly and fade like underwater flowers, other builders work with materials and timescales that dwarf such fleeting abundance. Rising from the seafloor around us, frameworks of living stone stretch toward the darkness above. Constructed not from death's sudden gift, but from the accumulated patience of countless tiny architects working grain by grain across millennia. These are the cold water coral reefs, forests built not of wooden leaves but of calcium carbonate and living tissue, growing in absolute darkness without any dependence on sunlight or the colorful algae that power their tropical cousins. Where the brilliant reefs of shallow seas pulse with urgent life and rainbow hues, these deep architects work in monochrome, their pale branches spreading like winter trees frozen in mid-growth, each colony adding microscopic layers to its skeleton year after year with the patience that only darkness can teach. The coral Lophelia pertusa dominates these underwater landscapes, its branching colonies forming immense reefs that stretch for kilometers along continental slopes and seamount ridges. Each individual polyp measures barely millimeters across, yet together they construct three-dimensional cities that rival any terrestrial forest in complexity and exceed them all in longevity. Under our lights, the palette remains subdued, chalk whites, faint creams, occasional soft oranges, dusted with marine snow like powder settling on ancient monuments. These corals thrive where the seafloor grows rough and currents run strong, along underwater ridges that act like windbreaks in the deep, redirecting the slow flow of water and concentrating the precious particles that drift down from productive layers far above. Each night and day, their delicate tentacles reach into the passing stream, catching plankton and organic debris one microscopic morsel at a time. The process appears impossibly inefficient compared to the flood of energy that bathes surface ecosystems, yet over centuries, this patient harvest builds structures of astonishing scale and endurance. Alongside these, coral architects grow sponges that challenge every assumption about what living tissue can become. These are not soft, porous creatures, but intricate networks of living glass, their bodies constructed from microscopic needles of silica assembled into forms that range from delicate fans to towering vases. Glass sponges filter seawater with extraordinary efficiency, some pumping hundreds of liters through their bodies each day, capturing bacteria and organic particles while helping to circulate and clean the surrounding water through their endless, patient metabolism. The combination creates complex three-dimensional habitats in a realm where shelter typically remains scarce. Fish find hiding places among the coral branches, their movements slow and deliberate in the perpetual cold. Shrimp and crabs cling to skeletal frameworks while brittle stars crawl across surfaces like living constellations moving through a frozen sky. The biodiversity rivals that of the most vibrant tropical reefs, though here every creature moves with the measured grace of those who understand that energy remains precious and patience means survival. Seamounts, those underwater mountains rising thousands of meters from the abyssal plains, provide particularly rich foundations for these ancient builders. As deep currents encounter these obstacles, they sweep upward along rocky slopes, carrying nutrients and organic matter to heights where coral and sponge communities can intercept the flow. Over geological time, the seamounts become true oases of life, isolated worlds where species evolve in quiet independence, many found nowhere else on Earth. What strikes us most profoundly about these stone cathedrals is their paradoxical nature, immense fragility coupled with extraordinary endurance. Each coral branch, though constructed of solid calcium carbonate, remains brittle and easily broken. A single disturbance can destroy centuries of growth in moments, yet these reefs persist in places where almost nothing else can establish itself. Some individual colonies have been dated at over 4,000 years old, making them older than the pyramids. Their growth so gradual that human lifespans pass unnoticed in their slow expansion toward the darkness above. These deep-water reefs serve functions that extend far beyond providing habitat. They act as nurseries for fish species that later migrate into shallower waters, connecting deep and surface ecosystems through the patient circulation of life. Their intricate structures slow currents and trap sediments, helping to stabilize the seafloor, while their growth and decay stores carbon in calcium skeletons, locking it away for millennia in the ocean's vast accounting of atmospheric balance. To drift above one of these reefs feels like visiting a landscape sculpted by time itself, delicate spires rising from the seafloor like the ruins of an ancient civilization. The silence remains complete, except for the faint hum of our equipment and the occasional soft crack of coral shifting under accumulated weight, sounds that emphasize rather than break the profound quiet of this underwater wilderness. Sponges shimmer faintly in the current, their translucent forms ghostly but alive, and everywhere, tiny creatures navigate the calcium maze with movement somehow subdued by the gravity of the transformation they inhabit. Yet beneath every surface of these patient monuments, on each branch, within each pore, across every grain of settling dust, the true foundation of all deep-sea architecture. Invisible films of microbes condition every surface, whisper chemical messages to drifting larvae, and manage the delicate chemistry that keeps these stone forests alive. What appears to be built from coral and sponge alone actually rests on the work of countless microscopic engineers, the ocean's smallest hands drawing the first blueprints that everything else follows, shaping not just individual reefs but the chemistry of the entire sea through work. So fundamental, we rarely notice their presence, yet without whom every structure we've witnessed would simply cease to exist. The stone cathedrals we've witnessed, with their millennia of patient construction, conceal their deepest secret within the very architecture we've been admiring. Every coral branch, every delicate sponge spicule, every surface in the deep ocean exists within a living film of organisms so small they escape notice, yet so fundamental that without them, every structure we've encountered would simply dissolve back into the darkness. These are the ocean's invisible majority, microscopic engineers working in realms smaller than the width of a human hair, quietly managing the chemistry that keeps the entire planet breathing. Beneath every surface we've touched in our descent lies a hidden metropolis, biofilms, coat rocks, sediments, and living tissues like microscopic cities where trillions of bacterial and archaeal residents share resources, exchange information, and coordinate their work through chemical signals that drift between neighbors like whispered conversations. Under a microscope, these communities reveal themselves as intricate neighborhoods with distinct layers, outer cells handling the flow of nutrients from passing water, deeper residents focused on processing and storage, waste from one level becoming fuel for another in cycles of cooperation that make human cities seem chaotic by comparison. Where larger creatures must hunt for energy or wait for food to drift within reach, these microscopic chemists have mastered the art of manufacturing sustenance from the most unlikely materials. They are the ocean's ultimate alchemists, drawing power from the simple exchange of electrons between molecules in what scientists call redox reactions. One chemical surrenders its electrons while another accepts them, And in that molecular handshake, energy is born. It's the same fundamental process that powers our own cells when we breathe, but here it happens without oxygen, without light, often without warmth, using whatever chemistry the Earth provides as raw material for life. Some microbes breathe metals using iron or manganese instead of oxygen in metabolic pathways that seem to bend the rules of chemistry. Others feast on hydrogen sulfide, the same compound that makes hydrothermal vents toxic to most life, transforming poison into nourishment through patient molecular manipulation. A few live entirely off methane seeping from cold vents, while others extract energy from the slow, radioactive decay of elements buried in seafloor sediments, drawing power from atomic processes that operate on timescales longer than the evolution of complex life itself. These tiny extremophiles thrive in conditions that challenge every assumption about what life can endure. Around the scalding vents we visited, heat-loving archaea work at temperatures that would cook most proteins. Their enzymes built with molecular flexibility that allows function where other biological machinery would simply melt. In the crushing depths of the trenches, pressure-adapted microbes use the same piezolyte compounds we found in snailfish to keep their cellular processes running smoothly under forces that would compress rigid structures into fragments. Their collective influence operates on scales almost impossible to comprehend. Through networks of biogeochemical cycles, these invisible workers regulate the chemistry of the entire ocean, processing carbon, nitrogen, and sulfur in endless loops that connect the deepest sediments to the atmosphere above. One microbial community consumes methane leaking from the cold seeps we explored, preventing greenhouse gases from reaching the surface. Another group transforms that carbon into organic molecules that feed the tube worms and clams of chemosynthetic gardens. A third community breaks down organic matter and releases nutrients that eventually drift upward to support the plankton in sunlit waters far above our current position. Every ecosystem we've encountered depends on their patient work. The whale-fall communities exist within microbial frameworks that manage decomposition across decades, transforming bone lipids into hydrogen sulfide that powers chemosynthetic bacteria. The coral reefs grow on surfaces conditioned by bacterial films that send chemical signals to drifting larvae, whispering instructions about where to settle and how to begin building their calcium carbonate cathedrals. Even the abyssal plains function as vast microbial processing centers where countless tiny organisms work through sediment grain by grain, mixing oxygen and nutrients through bioturbation that keeps the sea floor alive. A single liter of the water surrounding us contains more microbial cells than there are people on Earth, each one a microscopic experiment in survival. Together outweighing all visible marine life combined, they communicate through molecular signals, coordinate behavior across vast bacterial mats, and even share genetic material directly, passing useful adaptations between species like neighbors, lending tools. When population density reaches certain thresholds, entire communities can switch their metabolism in unison, opening new chemical pathways or building different structures as if guided by collective intelligence. Their resilience borders on the miraculous. Microbes have been recovered from sediments millions of years old, still metabolically active after eons of patience, living in rock pores where nutrients arrive perhaps once every 1,000 years. Some exist kilometers beneath the seafloor in conditions that seem more like geology than biology, yet they persist, processing chemistry at rates so slow that their individual lives span longer than human civilizations. For all their importance, these invisible architects work in perfect silence, contributing nothing to the ocean's bioluminescent displays or acoustic landscapes, yet their influence shapes every chemical gradient, every nutrient cycle, every breath of oxygen that makes complex life possible. They were the first inhabitants of the deep, the original engineers who learned to harness energy from chemistry rather than light. and they remain the foundation upon which every adaptation we've witnessed ultimately depends. As we drift through water thick with these unseen multitudes, we begin to understand that the deep ocean belongs more to them than to any creature we can observe. They set the tempo for every process we've encountered, their patient chemistry providing the stable foundation that allows evolution to experiment with the remarkable forms we've witnessed. In their microscopic realm, where individual lives mean little but collective influence shapes worlds, time itself takes on the rhythm that will guide us toward understanding how life in the deep writes its stories, not in moments or seasons, but across the vast, unhurried spans of geological ages. The invisible multitudes we've discovered, working their patient chemistry across eons of darkness, have created more than just the foundation for life in the deep. They've established the rhythm by which everything else evolves, a tempo so different from the surface world that time itself becomes transformed into something slower, deeper, and infinitely more patient. Where microbial communities have maintained their chemical conversations for millions of years, the larger creatures that depend on them have learned evolution's most profound lesson, that in a realm of scarcity, endurance matters more than speed, and the longest stories are written one careful word at a time. The fundamental difference lies in energy's precious rarity, which reshapes every aspect of how life develops and changes. Where sunlight floods surface ecosystems with abundant power, driving rapid metabolisms and swift generational turnover, the deep subsists on the faintest trickle of chemical energy and marine snow. Each calorie becomes a treasure to be hoarded, each movement deliberate, each reproductive effort calculated across decades rather than seasons. A fish that might mature in 2 years near the surface takes 20 years here, its growth so gradual that annual rings become barely detectable whispers in bone and scale. This metabolic patience creates evolutionary laboratories unlike anywhere else on Earth. The Greenland shark, drifting through Arctic depths, embodies this temporal stretching perfectly, growing less than a centimeter per year and reaching sexual maturity only after 150 years. Some individuals may live beyond 400 years, their slow heartbeats marking centuries, while empires rise and fall in the world above. The deep-sea corals we've witnessed add mere millimeters to their skeletons annually, their genetic lineages persisting in the same locations for millennia, while surface species rise and vanish in evolutionary heartbeats. Isolation amplifies this temporal stretching into something even more profound. The deep ocean fragments into countless separate worlds, individual seamounts rising like islands, isolated trenches cutting valleys into different planets, distant vent fields that flare and fade across geological ages. Populations become separated not merely by distance but by physics itself, evolving in parallel universes where each community responds to slightly different combinations of depth, mineral content, and energy availability. This geographic separation creates what scientists call the deep sea's evolutionary archipelago, where each habitat functions as its own experimental chamber. The snailfish thriving in the Japan Trench cannot survive in the Mariana Trench despite similar depths, because millions of years have fine-tuned each population to its exact chemical and physical environment. Amphipods from one cold seep prove unable to colonize another just kilometers away, their biochemistry calibrated to precise gradients of methane and sulfide that vary between locations like molecular fingerprints. Yet, this isolation also preserves evolutionary treasures that surface extinction events have erased elsewhere. The coelacanth glides through deep caves off Africa and Indonesia with the methodical stroke of fins that trace lines last drawn in ancient seas, its heavy, oil-filled body perfectly suited to the patient rhythms of the abyss. Its slow heartbeat, minimal metabolism, and year-long pregnancy represent evolutionary solutions so well-balanced that natural selection simply stopped tinkering, leaving these ancient fish as living museums of Devonian oceans. Reproduction in the deep operates by entirely different rules than surface mating. Many species reproduce only once every few years, producing large, energy-rich eggs designed for long journeys through crushing depths. The deep-sea anglerfish has evolved perhaps the most extreme solution to finding mates in endless darkness. Males are born as tiny, mobile creatures that must locate and permanently fuse with much larger females, becoming little more than reproductive organs attached to their partner's body. This ensures that when the rare opportunity for reproduction arrives, both sexes are guaranteed to be present, eliminating the impossible challenge of finding a mate in billions of cubic kilometers of dark water. The deep reveals a remarkable paradox. It serves simultaneously as Earth's evolutionary museum and its experimental laboratory. The profound stability allows ancient lineages to endure unchanged for hundreds of millions of years, their forms so perfectly adapted that mutation becomes disadvantageous. Yet, alongside these living relics, the abyss also nurtures innovations that unfold across spans of time that dwarf human history, creating anglerfish with living lures, loose jaws with private red flashlights, and snailfish that have traded rigid bone for the poetry of perfect pressure adaptation. Most deep-sea species cannot travel as adults, so they rely on larvae to carry their lineages across the abyss. Tiny, transparent, and patient, these microscopic travelers drift with currents for months or years, letting the ocean decide where they will establish new populations. Even objects become vehicles for genetic exchange. Sunken wood, whale bones, and volcanic pumice serve as slow arcs, ferrying entire communities between chemical oases separated by thousands of kilometers. As we contemplate these vast temporal rhythms, we begin to understand that evolution in the deep is less competition than conversation, a patient dialogue between life and the planet's deepest processes that has continued uninterrupted for billions of years. But this ancient dance now faces something unprecedented: the arrival of curious visitors from the surface world, carrying lights into darkness and questions into silence, beginning to write new chapters in the story of the deep through the careful art of exploration that seeks to understand rather than disturb the ocean's most patient secrets, the ancient conversations between life and time that we've witnessed playing out across geological ages in the deep's patient laboratories now face something unprecedented in their billion-year history. Into this realm where evolution measures progress in millennia, visitors have arrived from the surface world, carrying lights that have never existed here and curiosity that burns brighter than any bioluminescent display. We come as guests to a library written in slow water, learning to read stories that took the planet eons to compose. For most of human history, the deep could only be imagined, a realm of legends populated by monsters and lost cities. Then curiosity learned to listen before it tried to see. Weighted lines gave way to sonar, single pings evolving into sweeping fans of sound that sketched mountains no eye had ever met. These acoustic portraits revealed that our planet's most dramatic geography lay hidden beneath the waves, waiting for eyes brave enough to make the journey downward. The first human visitors descended in the 1930s within steel spheres barely large enough for two people. When William Beebe and Otis Barton reached 900 meters in their bathysphere, peering through tiny portholes, they became the first humans to witness the living light we've encountered, watching jellyfish pulse in patterns no surface dweller had imagined. Their brief glimpses opened a door between two worlds, proving the abyss was alive with possibilities. In 1960, the Trieste carried Jacques Picard and Don Walsh nearly 11,000 meters down to Challenger Deep. Their 5-hour descent through crushing darkness ended with a sight that changed everything: a small flatfish gliding across the mud at Earth's deepest point, proof that life's reach exceeded our most optimistic estimates. That single fish, moving with unhurried grace where conditions should forbid existence, became a symbol of evolution's endless creativity. Modern exploration has evolved from courage in small capsules to precision guided by technology. Submersibles like Alvin and Limiting Factor dive to crushing depths with relative ease, while remotely operated vehicles serve as our tireless eyes, connected by fiber-optic umbilicals that carry real-time images from places no human has visited. Autonomous vehicles glide silently through the water, mapping seafloor textures with unprecedented detail before returning to upload their discoveries into our growing understanding. Yet this growing capacity to see comes with profound responsibility. The deep calm disguises how delicately it is built. Sediment settles over centuries. One careless pass can leave marks lasting decades. Coral forests that took millennia to grow can shatter in moments. Even our sounds become footprints in a realm where whales navigate by hearing and fish communicate through vibration. The challenge is learning to explore with the same patience the deep has taught its inhabitants. Climate's subtle changes reach even here. The ocean absorbs excess atmospheric heat, and that warmth slowly filters downward, shifting how water layer and oxygen circulates. Proposals to extract minerals from abyssal plains or harvest methane from frozen hydrates promise resources but carry risks we barely comprehend. The deep economy of millimeters and centuries cannot repay debts quickly. So a different ethic has emerged among those who venture down, observe gently, share discoveries to minimize repeated disturbances, and recognize that the greatest explorations come not from conquest, but from listening. Each dive becomes an exercise in restraint, collecting only what cannot be learned through patient observation, understanding that we are guests in a realm operating by rules older than complex life itself. The deep still holds countless unknowns. Less than a quarter of the seafloor has been mapped in detail. New species appear with every expedition, and behaviors like navigation without sight or reproduction across impossible distances hint at forms of existence profoundly different from our own. But this isn't cause for urgency. The unknown endures as comfort rather than challenge, reminding us that mystery lives not in distant space but beneath our feet. Now let the ascent begin as slowly as our descent. The weight above lessens one invisible layer at a time. Darkness softens toward blue, then silver. The timeline we entered, measured in centuries and geological breaths, returns to the gentle rhythm of your own lungs. Pressure loosens into calm, and sound gathers into a quiet hush as we rise through zones we've traversed, each meter carrying us closer to the surface world that seems impossibly bright and hurried after our journey through patient darkness. Somewhere far beneath, vents still breathe chemistry into the night. Coral branches add microscopic rings. Microbes continue their tireless work, and whales trace the world in echoes. The ocean keeps its watch, unhurried and immense, turning over its memories with the patience of centuries. Above coasts and cities rest. Below, the ancient engine hums. If sleep comes now, let it arrive like a tide returning to slack water. Let thoughts drift as plankton drift, unhurried and unafraid. In the dark, the world is quieter than it seems and more alive than it looks. Sleep well. The ocean will keep its watch, and the whispering scientist will be here when you wake, ready for the next gentle journey into wonder.